Hey, it's Jim, and this is FRM Part 1, our book on quantitative analysis and the chapter on random variables. Let me give you the statistical definition of a random variable. It's a mathematical function that assigns a value to random phenomenon. And that random phenomenon for us in this risk management and quantitative analysis topic could be a recession, a default on a loan, a spike in oil prices, etc., etc. Very quickly, as I'm thinking about the types of questions and the amount of questions that GARP can ask you inside of this chapter, what I'm thinking about is mostly from a definitional standpoint. And of course, the obvious one is the two types of random variables, discrete random variables and continuous random variables. I give my students lots of examples, but among my favorite, and maybe this will help you guys distinguish between the two, because I do think that's a really good exam question. Those of you who are horse racing fans, you'll know that first Saturday in May we have the Kentucky Derby, and the people in charge of it, they limit the number of horses in the Kentucky Derby to 20. Now, many years there's maybe 18 or 19, but some years there are 20, depending on scratches. And so let's suppose there's 20, 1 to 20. Which of those horses is going to win? That's a discrete random variable because, well, only 1, 2, 3, right, all the way out to 20. You can't have 25 in there. So that's a discrete random variable outcome of the Kentucky Derby. But the time of the Kentucky Derby, the winning time, that's a continuous random variable because although there's, of course, the Great Secretariat was the first and maybe the only horse to run it under 2 minutes, but you could run it in 2 minutes and 1 second or 2 minutes in 1.1 or 1.2 or 1.3. I mean, right, so that's a continuous random variable. Know the difference between those two. I think that'll help you on the exam. The learning objectives, what's that, 6 of them there? We'll talk about probability mass functions and cumulative distribution functions. I'll show you a couple of pictures, and I think the illustrations really help distinguish between those two. We'll talk about expectations. We'll do mean, standard deviation, skewness, and kurtosis. Those are the moments of a distribution. We'll talk about quantiles and linear transformation towards the end. So my advice is to pay attention to the definition of all of these. Although notice the action words are not defined, but I feel like GARP is limited inside of this chapter from a mathematical standpoint, although it gets into some of this other stuff in later chapters. But I think definitions are good here. So I gave you that statistical definition of a random variable. Let's go ahead and adjust that a little bit to kind of a risk management conversation that we're having here. Uncertain expected future values. So we've done some basic time value of money stuff where you have $100 today. You invested at 10%, you can expect to have $110 at the end of the period. Let's say it's a year, but that future value is an expected value and it depends on the interest rate. I mean, interest rates might be 10% today, but they might not be 10% tomorrow or any time during the course of the period. Now, you could have a guarantee from a bank or some investment firm, but what if that bank or investment firm goes bankrupt? So even guarantees are not really guarantees in the financial sector. So there's another definition as it relates to risk management. So think about the uncertainty of future values, which could mean something as simple as future value of a portfolio for retirement, or hey, we can go ahead and spend some good time talking about how to calculate value at risk today over a 1-day window or maybe a 2 or a 3 or a 10-day window. But of course, good risk management involves the question, okay, what might value at risk be at the end of this 10-day period, moving forward to the next 10, call it a rolling value at risk. So there's all sorts of uncertainty out there. Of course, notice the illustration that we have. There's a roll of the dice over there, or the flip of a coin, or a lottery ticket. So I'm not much of a gambler, but I'm guessing if you go and you throw the dice, people know what they're doing. Of course, James Bond in that great Diamonds Are Forever movie, he was at the table and he threw, and of course he won. James Bond always wins in gambling, in case you guys didn't know that. Here's this slide on the differences between discrete and continuous. So there's the dice or the die, right? Let's make sure we do plurals and singulars. And so there's the probability going across, right? There's only 6 possible outcomes. This is discrete, just like there's only 20 possible horses that can win the Kentucky Derby. And that probability, of course, is defined with the roll of the dice as somewhere between 16 and 17%. Continuous random variables, on the other hand, are continuous. Look at the graph there. Well, back here, we had a horizontal flat line going across at 16.7%. Here we use squiggly lines to define continuous because we're not quite sure what those things can be. We know back here that it's random that we roll a 2 or a 4, but those probabilities are the same. Here, stock price or value at risk or an interest rate can be almost anything. Now, one of the things that is very interesting about the difference, and this is what I was telling you about definitions, is that with the roll of the dice, you know that you have the same probability of each one of those 6 possible outcomes. But you can't say something like, oh, we have a continuous random variable, let's just pick interest rate. What is the probability that some interest rate is going to be 5.827%? You can't really do that because 5.827 could go out, another 100, what do we call those, significant digits. So you can't do that. So what we do with continuous random variables is we say something like, okay, we can't identify that point, but we can identify something between 2 points, a probability of an event occurring between 2 points. Let me give you a quick example here. If you ask me, what's the probability that a company like, let's say Microsoft has a total market value of 2 or 3 or 4 trillion dollars, however large these companies are these days, I would have to say, well, I really can't give you that probability, but I could say, what's the probability of Microsoft having a market value of between 2.8 and 3.2 trillion dollars. So that's why that bottom bullet point there says within a given interval. And what we can do is we can establish whatever those intervals are. Look at the second bullet point up there. We can have x could be greater than 0. We could have it be between 0 and 1, which of course leads us to probabilities, or it could be between a minus infinity and a positive infinity, although if you can explain minus and positive infinities to me, I'm all ears, because that's one of those math concepts that, it's a pretty big number, but I really don't know what that number is. All right, moving on to this learning objective statement that asks us for distinguishing between probability mass functions and cumulative distribution functions, and explain the relationship between these two. So this is another one of those definitions here. So the probability function, just very basically answers the simple question. We have an event. We know that it might not occur at 0. We know that it might occur with 100% probability at 1, like the default on a loan. But the default on my mortgage loan is the probability of default on my mortgage loan is probably different than the probability of default on lots of other mortgages out there. So how is that distributed depending on, all sorts of underlying factors? Now, one of the questions at the end of this chapter is this second orange teardrop point here. 2 probabilities of two key properties of a probability function is that, of course, they've got to be between 0 and 1 probabilities, and the sum of them must equal 1. There's a giveaway to one of those questions at the end. So there are two types, a PMF and a PDF, and this depends entirely on whether the random variable is discrete or continuous. So the probability mass function, that's for a discrete random variable. So notice the illustration that we have, this graph, we've got a 0 and a 1. We're using the Bernoulli random variable model. And so Bernoulli, this is a specific case of a binomial model. And so it can either take the value of 0 or 1. For example, Tiger Woods can either make the putt or he can miss the putt. A loan can either default or it cannot default. So we need to have probabilities of success. Notice in this case we've got a P of 70%, so probability of failure has to be 30%. And so there's the function there inside of the graph. All we're going to do is take the P probability times 1 minus P, which is 70% times the 30% in this particular case. And we're going to raise it to, some value of X, which is going to be either 0 or 1 in this case. And so there's the picture, right? We've got 0, 30%. We've got 1 at 70%. So there's the Bernoulli. And by the way, we're gonna have a chapter in the relatively near future where we're gonna have to talk about all different types of random variables. The Bernoulli will be a good one, but we'll wait to talk more details about that to a future chapter. All right, so remember that the PMF, that's discrete, then the PDF, that's continuous. So with continuous, we're going like this, or however we want to draw it. We're going to rely on our knowledge of calculus and being able to integrate. Now, the good news for you guys is that we'll have to do some calculus as we go through the program, but not this early in book 2. And so all we're doing here is remember what we can assign a probability for some kind of a range. So there's an A. So look inside the blue box. There's an A, and then there's a B. So that was, what did I say with Microsoft? 2.8 trillion and 3.2 trillion. And we can say, all right, there's going to be some probability inside. And has to be in between those two values. There's the integral sign, there's the A and the B, and then the function, and then the dx. That's always just stands for, hey, we may have to change this thing as we go along the function. So let's take a quick look at the pictures down there. Let's look at the middle picture for the normal distribution. Remember, you guys don't know this yet, but maybe you know this from previous conversations, that a normal distribution can be defined only by its first two moments. All we need is the mean and the variance to describe a normal distribution. So if you put a mirror right there at the peak, the mirror is a perfect image of each other, of the other side of it. So normal distribution, what we can do is we can say something like, where are we defining that range? And that range could be almost anything that we want it to be. And you can do this for the uniform and the exponential distributions as well. All right, so what we're doing up to this point is trying to figure out probability of a range. But it's also interesting to ask the question, well, suppose we start all the way over at the left-hand axis. And let's just start adding some probabilities together. What's the probability that we get between 0 and 0.1? What's the probability that we get between 0.1 and 0.2? 0.2 and 0.3. I mean, I just picked those. Those are easy deciles right there. So the cumulative distribution function is really just a matter of adding. We're going to add one range to another range to another range, but we start at the origin. So if we look at the very bottom, we can look at the cumulative distribution function for the Bernoulli random variable from the previous page, and there's the 0, there's the 1 minus p, so there's that probability of success, and there's the 1. And by the way, of course, look at that orange teardrop point. Both continuous and discrete, they have cumulative distributions. So here's this Bernoulli picture of, here, let me go back here real quick. So there in the bottom blue box, there's the, kind of the function, and here's the graph. So if x is less than 0, there's no way that can occur. If x is greater than or equal to 1, there's no way that that can occur. So really, we're just doing the steps, take the step up. So there's the, at the 30%, and then all the way, and then if you add the 70%, so 30% plus 70%, that gets you 100%, right? So there's the step of the CDF for Bernoulli. What does it look like for the continuous function? Well, notice we're integrating from a minus infinity, so that gets us all the way over to the left axis, all the way up to A. So once again, let's look in the middle normal distribution, that bell-shaped curve. So there's A somewhere to the right of the mean. Remember, the mean is going to be at the peak. And so what we're saying is that, hey, what's the cumulative distribution function look like at, pick some number out there. What did I say with Microsoft? How about $2.6 trillion? And so you can determine the probability that Microsoft is going to have at least a 2.6 did I say million or billion? $1 trillion market value. And of course, you can do this for exponential and uniform functions. Now look in that red box there. This is what I was telling you about just a second ago, that all we're doing is adding. So here's that, we're just summing. There's the sigma sign. So we're just summing all of the PMFs. And so we do that all the way from the left-hand side all the way to, whatever range, whatever value that we want. And then what we can do is we can compute the difference between consecutive values of x. So there's the f at x and the f at x minus 1. This is going to be super important in a relatively near chapter when we talk about, and let me give you my example here as a 63-year-old dude who's getting ready to turn 64. What the insurance people can do is they can say, all right, let's just suppose Jim's 64. What's the probability that Jim is going to die during the next year of life? So we look at the mortality tables and we figure that out. But then we could say something like, all right, what's the probability of Jim dying in the next 5 years? Okay, so we can look at the mortality tables, we can do that thing. But then we can ask the question, and this is the difference between consecutive values, what's the probability that Jim is going to die between 65 and, what is that? What did I say, 5 years? So that's 69. Then we have to take the difference in there. Now the mortality tables are going to kind of do this function for us. And so that'll be interesting conversations. But this is important here, the difference between consecutive values of x. All right, how about the learning objective on the mathematical expectations of a random variable? So all we're doing is saying something like, let's suppose that we have some random phenomenon. Like, how about if I do another example with me? This will give you guys some comedy relief. Suppose we pick a professional golfer, Rory McIlroy or Scotty Scheffler or Jordan Spieth. So we pick one of those dudes and we put him on the green, and it's a 12-foot putt. And we ask him to try to make that putt. And then we ask me to go to try to make that putt. So what's the average? What is the expectation for, let's say, Scotty Scheffler versus the expectation for little Jimmy over here? Well, of course, we both have a ball, right? It's the same ball. It's the same putt on the same green. We have similar putters, right? And we go back and we hit it. But clearly they have a much higher probability. My point here is that the mathematical expectation of the expected value, the mean value, we can't just say, oh yes, Jim and Rory have the same probability of making that putt, because we have clearly different skill sets. These are professional golfers. I stink at it. So that expected value is a probability weighted average of all of those possible outcomes. So we have the dark blue box, that's for the discrete random variable. And so all we're going to do is take the probability times each one of those random variables, and we're going to add it. So look in the end, there's the summation sign. But for a continuous random variable, we need to integrate. Let's do just a quick example here. 8 different positions. So we've got 3 of them worth $1 million, 2 of them worth $2 million, and then the remainder are worth $3 million. What's the expected value of the bank's trading book? So this is super simple, and you don't even need that. You don't even need that f of x in there. So look down at the bottom here. So the expected value of the portfolio, the expected mean value. So all we're going to do is take a probability weighted. So we've got 3/8 and then 2/8. That's 1/4, and then 3/8, and we're going to multiply each of those by $1 million and $2 million and $3 million. And so if you do the math quickly, that's $2 million. This is probably the limit of what I think GARP will ask you in terms of a math question inside of this chapter. Now, I'm going to pause on that and say, wait a minute, Jim, didn't you take a look at those 10 questions at the end of the chapter? And of course I did. And there are a handful of questions in there that say something like, hey, calculate mean and standard deviation. I'm hoping you guys can do that in your financial calculator. If not, I'll show you that when we get to it in a later reading. But the GARP also asked you to compute some of these ranges that we'll talk about. All right, how about properties of expectation? This is one thing, another definitional question that I think is important. So there's linearity between x and y. Expectation of a constant is just the constant. You can scale it, so you can bring out whatever that scalar is. Here it's a. If you have independent variables, this is important. You can move that expectations operator through the x and the y, and the expectation of an expectation. You can't have a double expectation. And the expectations operator, you can't move through non-linear functions. So let's hit this learning objective on the 4 moments. I told you there's the mean. So there's the mu, that's the expected value of x. There's the standard deviation. Remember, standard deviation is simply a measure of the degree of error. So let me give you just a quick example. If we expect the interest rate on a time value of money problem to be 10%, so we go from $100 out to $110, we're expecting 10%, but we know that economies, they can contract and they can expand, so that 10% is going to change. Well, what does that mean? That means that at the end of the year, maybe we'll only have $108, which would be 8%. Maybe we'll have $113, which would be 13%. So we need a measure of that degree of error. I mean, imagine if you thought you were going to get 10%. You planned to get 10%. And at the end of the year, you got 10%. Oh my gosh, everything is perfect. But what if at the end of the year, not only did you not get 10%, but you lost 100%? You see the difference between those two examples. That's a standard deviation of 0 and a standard deviation of, well, I have no idea how big that standard deviation is, but it's massive, right? So all we do to compute that second moment, the variance, and remember the standard deviation is the square root of the variance, is we say something like, okay, we expected to get 10% and we got 13%. Let's take the difference between those two. So 13 minus 10, that's 3, and then we square it. And then we add up all those kinds of things, and we take the square root, and we get the standard deviation. So my point here is, remember that the first moment gives us kind of like that idea about what can we expect to happen. But then the second moment tells us how wrong we can be. So if the standard deviation is low, that means that there's very low risk. If the standard deviation is high, that means that there's very high risk. It's as simple as that. Now look at the picture in the middle. This is a normal distribution. Well, let's call it a symmetrical distribution here as we move to the third moment. That means that the mean, the median, and the mode, remember the median is the one that's, when you're driving down the road and there's a median in there, that's the thing in the middle. The mode is the number of time, the number of outcomes, the number that appears most frequently. So when those three things are identical, then we have a normal distribution or a symmetrical distribution. But sometimes we're skewed over to the left and sometimes we're skewed over to the right. And that's when we have positive skewness or negative skewness. And so there's the orange equation. I can't imagine that you would have to compute skewness on your financial calculator, but there it is. I mean, instead of back here, you just take those difference between, what was that, the 13 and the 10, and you square it. Here, you take the difference between the 13 and the 10, and you have to standardize it by the standard deviation, which you just calculated with the second moment, and then you have to raise it to the third power. So imagine if you had, like 5 outcomes, and you'd have to do this. I don't know. It just seems to me like that just takes too long of a time. I think the more interesting question is, okay, what happens if skewness is this number or that number? What happens if the mean is greater or less than the median or the mode? So my advice is just to get your camera out, take a picture of this slide, so that when you see a picture, you'll know, oh yeah, positive skewness or negative skewness. Now, in the future, we're going to have really great conversations of whether things like, hey, are stock returns, are they normal? Or do stock returns have skewness? And do they have kurtosis, which we'll do here in just a second? And if stock returns have third and fourth moments in there, well, then that changes the kind of risk management models that we can use. Or there's the fourth moment. So you might expect, boy, if my lectures are making any sense, you would think, okay, let me go back here. Second moment we squared, third moment we cubed, fourth moment we fourthed. Of course, that makes sense. But the great question here is when you have kurtosis, you can either have higher means, right? See, there's the orange, or lower means, there's the green, and heavier or lower tails. So I would remember those three terms there. You see in the box on the right, mesokurtotic, leptokurtotic, and platykurtonic. Now, that's the term, those are the terms that I learned back in the old days, but apparently they've cut them off, so it's just mesokurtic, leptokurtic, and platykurtic. But hey, either way. Oh, and by the way, the normal distribution has a kurtosis of 3. You can't do this back here for skewness, but normal distribution kurtosis of 3 greater than, that means it has the heavier tails, less than has the thinner tails. Oh, by the way, this is super important. So notice in those bottom 2 bullet points, higher probability of extreme events, lower probability of extreme events. Oh my gosh, this is a great exam question where the GARP could say something like, okay, let's go back to 2007 and let's pretend that everything is normal for the next year or so. All of a sudden we have the 2008 financial crisis, and what happens? Oh my gosh, we've got this left-hand tail that was way more massive than we had originally thought. So remember the relationship between the lepto and the platy and these extreme events, and then how they increase the importance of things like value at risk and expected shortfall. When I teach my investments class, we'll calculate standard deviation, and I don't make them calculate skewness or kurtosis, although I make them memorize, the definitions. But then I go ahead and say, all right, let's go ahead and calculate correlation coefficients, because students they all know, because I have business students, upper level finance students, so they know about correlation coefficient. And then I go back and I say, well, how did you calculate correlation coefficient? And the students will say, well, you know what, Jim, we got out Excel and we put them in a spreadsheet and we hit the correlation function. I'm like, all right, how do you do it the long way? You can't calculate a correlation coefficient by itself. What you have to do is calculate covariance. So the covariance between two stock returns, let's say Coca-Cola and Pepsi-Cola, right? Well, we go out and we get some stock returns, and what do? Before we calculate correlation coefficient, we've got to calculate the covariance between those two random variables. Well, I tell my students that, look, when you calculate the covariance between those two stock returns, you could get almost any number. You could get a negative 455, or you could get a negative 0.397, or a positive 16. And I asked them, I say, all right, interpret that for me. And they're like, well, Jim, I'm not quite sure what that means. And of course, so a lot of times, these random variables, they don't have natural and intuitive interpretations. So what do? We standardize the random variable. And anytime you standardize a random variable, you divide it by some measure of the degree of error. So look over here, the standardization technique. In fact, this is where we get the word standard, is by dividing that numerator from all of our moments there by the standard deviation. And so Z, that's our standard normal distribution. And it has a range of 0 to 1. So this is where we use all of these probabilities. And this is super important as we go through the rest of Book 2 in quantitative analysis. We're going to refer to the standardized normal distribution function thousands of times. Thousands, that sounds like a lot. All right, so remember back in Book 1 where we did capital asset pricing model, then we did the arbitrage model, and then we did data aggregation. And we were trying to say, all right, we got all this data. How can we compress it? Well, one way is what we just did on that previous slide. We can standardize it, but a lot of times after we do something like clustering, some kind of artificial intelligence, some kind of reduction technique, whatever that technique is. So we've reduced our data. Now what can we do with it? Now, well, the next step, or a step, is to chop it into different parts. You can chop these quantiles into as many as you want. You can chop them into fourths, which are called quartiles. You can chop them into fifths, which are called quintiles. Into tenths is deciles. Into 100ths, that's percentiles. I'm a big believer in percentiles. Let me give you some advice here. You ready for this? Next time that you see somebody and you should know their name, and you quickly ask your friend, you say, hey, what's that dude's name over there? And they'll say, it's Ed. And you have to ask the follow-up question. You have to say, what's your percentile on that? If they say 100%, then you know it's Ed. If they say 95%, well, then you're in trouble. Do you want to take the risk that dude's name is not Ed? That's 5%. Wow, we're going to talk about, I picked 5% as an important number there. We'll talk about a 95% confidence interval, maybe 99% anyway. So my point is, you can chop this into any kind of a number that you want. Notice in that first diamond point there's the alpha quartile smallest number. There you go. You can see it inside of that first orange box. If we have a continuous random variable, then the median has to be right in the middle. So we go from that minus infinity all the way up to, whatever we pick, whatever we define as M. But the important questions are on the exam is probably going to be this interquartile range. So remember we just talked a little bit about standard deviation. What did I call that? The degree of error. Well, if we want this interquartile range, what we can do is we can say, okay, 25% here, 75% here. So think about what that means. That's the 50% in the middle. What the interquartile range does is it adds value to our assessment of risk. Remember I said standard deviation is the degree of error. Well, the interquartile range also is some measure of a degree of error, but inside that 50%, call it the meat, right? The meat of the distribution. How about another quantile-based estimator, the mode? You can have unimodal, where there's just one mode. You can have two modes. You can have multiple modes. Now I'm going to show you a picture here in just a second of this quantile function. It's the inverse of the cumulative distribution function. And I have my students, when we in my investments class, we use the norm dist and we use the inverse function. It's pretty cool stuff. But what this quantile function does is it maps, some probability that relates to, what did I say with the Microsoft, the 2.8 or the 2.6 or the 3.2, whatever that thing is. And what we can do is we can interpret that as the value below whatever that alpha number that we pick. Here we have, what is that, the 80th percentile, but it could be almost 80th, it could be almost any percentile. So this relates to that summation in that cumulative distribution function that I was talking about earlier. But then what you can do is you can do this same thing in between the 25 and the 75th percentile. This is going to be the interquartile range. So here's this picture that I was telling you about. So here's the quantile function, and we just use, anything could be on the x-axis. Here, notice in parentheses, we have value at risk. And so we have chopped this from 0.2 to 0.4 to 0.6 to 0.8. So there's the quintile, right? And so notice it goes up like this, and then it goes all the way until it hits the 100%. Now, if you flip the axes, you get the cumulative distribution function. Let's continue our discussion on these quantile-based estimators. The most common are the median, the one that falls in the middle, the percentiles, what I was talking about just a second ago about finding out people's names, and that interquartile range. Now, the important thing is that these quantile-based estimators are extremely helpful when we look at that left-hand tail of the distribution. What did I say earlier? We want to compute, let's say, a 95% confidence interval. But beyond that, we want to have what's the value at risk at 98% or 99%. We want to know what's the worst thing that can happen. What's the probability of the worst thing that can happen? And then what's our loss if that worst thing does occur? This, of course, is the job of the chief risk officer. All right, so let's take a look at a little bit more detail of these. The median, that's the central quantile. That's the middle of the value, so half above, half below. The median is not distorted by outliers, so that's a really good exam question right there. The interquartile range, so this does that middle 50th percentile, but notice that bottom bullet point down there. It ignores the tail of the distribution. So think about the value. What we're doing now is separating what goes on in the tail, right? The left-hand tail, worst case scenario, versus what goes on sometimes always in the middle. In other words, if we have kind of a normal economy, what does that spread, what does that range look like? We have to be prepared for these massive negative events, but of course we also have to be prepared for just regular old normal economies, regular old normal default rates on student loans, regular old normal default rates on automobile loans, right? So as good risk managers, we've got to be prepared for regular stuff and for outrageous outcomes. All right, let's take a look at this last learning objective. Why on earth would we transform a random variable? Why would we linearly transform a random variable? Well, what it does is it makes the data more manageable, right? More interpretive. It makes it, we can make more sense of it. We can do more stuff with it by transforming these variables. This is super important in risk management. So what we're going to do is we're going to add one or more of major math operations. We're going to add a constant, we're going to subtract a constant, we're going to multiply, or we're going to divide. Aren't those the four things that you learned back in kindergarten? That's what I learned in kindergarten. Of course, I make it up. Now notice that last bullet point down there, the embedded bullet point. So when you transform these variables, it results in a new random variable. So the question then becomes, is that new random variable any better than the original random variable? And the answer is, it can be. It doesn't have to be, but yeah, of course, many times it is. So here's a quick example here. We've got alpha dollars per year as our salary, and we have B dollars as a bonus. So X is going to be something that sounds like, hey, what can you sell during a certain year? In other words, how much are you going to make at the end? So we transform the sales variable and add the Y variable. And so this is just a linear transformation of two variables into a regression analysis. So we say that our total amount made, which is our new transformed variable, is equal to some kind of a constant, right? That's our salary, that's a constant, plus some adjustment for a bonus. So if X is 0, then we just make our salary, right? We just make the alpha. We make the vertical intercepting term. Now the question then becomes, how does that affect the moments of the distribution? Well, if we take the expectations of Y, that's our new variable, that's our total income, total compensation. Well, remember what we said earlier with that slide on what happens to the expectations operator? Well, the expectations of a constant is the constant itself. So there we have the equal sign, that just equals alpha. And then if we take the expectations of B, of this B dollars, you get a bonus of B dollars every time. Well, what you can do is you can extract that constant out. So the expectations of your total compensation is equal to, of course, your salary plus how many units do you think you're going to sell? What is that expected? I mean, it could be 1, it could be 30, it could be 500, and you just multiply that by the other constant of beta. Then the variance, based on the variance of Y, based on those expectations above, all we're doing is taking the variance of alpha plus beta X. Well, if you can do some good math over there, and that gives you B squared times the variance. Standard deviation, of course, let's just take the square root of that, and we get some indication of what's going on with the third moment of the distribution. So notice those two diamond points down there. We've got B is positive, that has one thing. If B is negative, well, then that has another implication for skewness and kurtosis. I would memorize this slide as well. And that takes us through lots and lots of definitions, some calculations. I did say earlier I would get back to an interquartile range. So what I want you to do is go look at those 10 questions at the end of the chapter. You ought to be able to go through a bunch of them pretty quickly, but you do have to calculate some. So even though the chapter didn't tell us how to calculate mean and standard deviation, it asks you to do that. So I bet a lot of you know how to do that with your financial calculator. But then spend some time on questions, 8 or 9 or 10, whatever those are, computing those extra calculations, and you should be fine. So hey, thanks for watching. Have a great day, and as always, good luck studying.